This video is the first of probably several looking at lighting in WebGL. We're starting with directional diffuse lighting. This is the first video that viewers may consider more advanced, because I will be introducing what will probably feel like a lot of new concepts and functions, and that can come across as overwhelming. But when you strip things down, it's really only 5 or 6 new things that you have to learn here, and half of them should end up feeling just like common sense. So I hope that at the end, this will feel like a sudden tiny step up and not a long, steep learning curve. Anyway, that's my hope. Here are the 3 fundamentals that, if you can commit to memory, will make diffuse lighting much easier. We'll go over each of these in more detail over this video. The dot product gives us our lighting value. It calculates a single number that represents the brightness of a particular part of our mesh. Normals are a way to specify or imitate orientation information for a surface, or the way a surface is pointed. And the inverse transpose, not always necessary, but is a matrix transformation which you need to use if you have a model or view matrix that significantly deforms your objects in certain ways. Here's how we're going to step through this. In part 1, we'll look at calculating a brightness value using the cosine emissions law. We'll then look at dot products as a way to shortcut calculating cosines. We'll look at normalization as a way to keep our vectors a consistent length. And we'll look at vertex normals as a way to represent or simulate surface orientation. Once we have these under our belt, we'll be using these ideas to build our first simple lighting model. This is the point where we're sort of done, because the rest only really has to do with fixing problems, mostly with our normals. In part 2, we'll look at some of the problems we run into when we transform our models without updating our normals. We'll look at using the model matrix itself to fix simple problems, and using the inverse transpose as a way to fix major problems, mainly when our objects are significantly deformed. And last, we'll look at smooth shading and how normals aren't always 90 degrees to our actual mesh surfaces, and the differences between vertex shading and fragment shading. I hope that you'll make it all the way through here. It's a lot to go through, so this video is a lot longer than most of my others, but I hope everyone will get at least something out of this, even if you bail out before the end. For part 1, here's the code that we'll be building up to. This is the simplest version of directional diffuse lighting that you can have. We're calculating a brightness factor here using just a single dot product calculation. We're using that to boost the base color of our object. In certain simple situations, this may be the only code that you actually need. So let's start. Okay, first up, the cosine emissions law, also called Lambert's cosine law. This is an incredibly simple idea. If you point a surface directly away from a light source, that surface will be dark, right? As you turn it towards the light, it will remain in darkness until it reaches 90 degrees to the light. After 90 degrees, it will become brighter and brighter. And if you point the surface directly at the light source, it will be at its maximum brightness. This relationship between the surface's angle towards the light as it goes from 180 to 90 degrees is flat. It stays at 0% relative brightness. And from 90 degrees to 0 degrees, it ramps up from 0 to 100%. And at 0 degrees, where it's directly facing the light, it's at its maximum brightness, 100%. And this relationship, it's not linear or exponential. This curve is actually sinusoidal. It follows the general shape of a cosine wave, or rather, only the positive portion of it. Okay, simple enough. So next we have to calculate the angle between our light direction and the way our surface is pointed. Thankfully, no. We're not interested in the angle. We're interested in the cosine of the angle, which I know sounds worse, but it's actually much better. Do you remember this mnemonic? You probably learned this in high school for the special case of right triangles. Cosine theta is equal to the length of the adjacent side divided by the length of the hypotenuse. So for that one special case, it's just a ratio of two numbers. And it turns out that there's another special case if you have two unit vectors. That is, two vectors with a length of exactly 1. Then their dot product equals the cosine of the angle between them. So in other words, the dot product of our surface direction and the direction to our light source is the cosine value we're looking for. The dot product of those two vectors is our brightness. So, okay, fine. What do you got to do to calculate the dot product? The good news is that you usually don't have to, not unless you implement your own matrix math library. WebGL's shader language, GLSL, has a built-in dot product function, so we can calculate this directly in our shader code, and every JavaScript vector library that you'll ever find should have a dot product function. But in case you want to do this yourself, the calculation is absurdly easy. Here it is in 2 dimensions, and 3 dimensions, and 4 dimensions. It's just a series of multiplications and additions, nothing complex. But again, for calculating a cosine, this is a special case, and it only works for unit vectors, vectors with a length of 1. Which brings us to the next thing that we need to understand, normalization. If you have a vector whose length or magnitude is not 1, or if you're not sure, normalization fixes that without changing its direction. Again, GLSL has this function built in, so will every matrix math library you'll ever find. So just call normalize and you're done. And in case you want to implement this yourself, again, it's incredibly simple. So now we've talked about normalization. Last, let's talk about normals. Similar name, totally unrelated meaning. There is a pretty good chance that you already know at least a little bit about normals. In tutorials and textbooks, they're often simply represented like this. If you have a flat surface, its normal is the direction the surface is pointed. On a solid object like this cube, the normal for each face would point outward, away from the interior of the mesh. Or if you're inside the cube, the normals would probably point inward. So it's a direction away from the surface. While we usually visualize a vector as a line, it's not a line. And though we usually show a normal as anchored to a face or a vertex position, it doesn't really have an origin either. It's simply a direction, like a heading or a trajectory. We usually represent normals in WebGL as a vec3 with x, y, and z components, and in this form they do describe a line that runs from the origin at 0, 0, 0 to that x, y, z position, but they're just a direction. And no matter what you hear me say or what you see later in this video, the thing to remember is that a normal is always perpendicular to its surface. That's basically its definition, and for lighting, it's an absolute requirement. So when you think of normals, you should always keep this visualization in your head. The thing is, well, 2 things. First, in WebGL, we deal in vertices, not surfaces. We use vertices to construct surfaces, and those surfaces will each have their own normal. But if we only used those surface normals for our lighting calculations, then all of our models would look like this. Lots of flat surfaces and angular edges. Sometimes that's absolutely what we want, but not always. And second, even if we wanted this, where would we assign our face normals? There are no buffer arrays for faces. No, for normals, we basically have just 2 choices. We can assign them once per vertex as an attribute. One triangle has 3 vertices. That means that each triangle has 3 normals. And though I won't go into it in this video, you can also pass in normal information in a separate texture image called a normal map. But for us here, normals are going to be going in as vertex attributes. So, one normal repeated 3 times for every triangle? Sounds like a lot of duplication, right? Well, yeah, for flat shading like this, yes, it is a lot of duplication, but that's actually okay. In fact, it's basically unavoidable. But we'll see later how we can use different normals for every vertex to achieve smooth shading. Okay, that's enough theory for now. Let's try this out. Remember, to light something, we're looking for a number, a brightness value. We get that value from a dot product of the direction to the light and the normal. and we're ignoring the value if it's negative. Surprisingly, we're going right back to the beginning to our Hello World example from our very first video. This program has no vertex buffers, and we're not going to add any, at least not for now. Just a single draw call that will create a single point primitive. I've blown it up big here, but this in reality is just a point in 3D space. And I'm just doing this to demonstrate that this brightness value has nothing to do with our geometry. It has to do with a normal and a light direction, which we're going to hardcode here. So let's begin in the fragment shader. Right now it's outputting the color red. Let's multiply this output color by a brightness factor. This will be a number between 0 and 1. 0 should give us no red, and 1 should give us pure red. We could calculate this number here in the fragment shader, but let's do it instead in the vertex shader. Why? Well, the vertex shader code will be run only one time, once for our single point primitive, while the fragment shader will be run once per pixel. That's 4,000 pixels. So in this case, it makes a lot more sense to do it in your vertex shader. So this will have to come into the fragment shader as a varying. We'll have to declare this varying in our vertex shader too. And for now, let's just hard code that value to 1. Seems to work. Next, remember, we calculate our brightness value using the dot product function. Let's do that now. We need a light direction and a normal. The light direction is the direction to the light. So let's make that up, to the right, and to the back. And for the normal, let's put it straight to the back. Okay, the square is still red. Change the normal so it's pointing in the opposite direction, and the square is now 0% red. But hang on, that's a bug. It shouldn't be 0% red, it should be unlit. It should be black. And the problem here is that our base color is an RGBA, which includes alpha, or opacity. So we're not just turning down the red, we're also turning down the alpha. To fix this, let's reset the alpha. Let's make another change. Let's make it so that 0% brightness still shows some of the base color. This is called ambient lighting. Ambient plus diffuse doesn't have to add up to 100%. Summing to more than 100% gives it a blown out, overly bright appearance, and summing to less than 100% gives the entire model a dark, underlit appearance. But let's do 20% ambient and 80% directional. Okay, hang on. 2 more problems. First, the red earlier should have been bright, but not 100% bright, because it was facing the light at an angle. And second, the color now should never be 100% black. It should be a minimum of 20% red. And this is due to 2 problems. First, our light direction vector is a lot longer than 1. An XYZ of 111 gives us a length of about 1.73, so we need to normalize that for sure. And second, remember that our dot product gives us a cosine value? Well, cosine values can be negative, and if it's negative, as it is now, it'll start eating in to the ambient lighting. So let's just set the brightness to 0 whenever the dot product is negative. Great, seems to be working. Underwhelming? Yeah, I agree. Let's try animating this. Let's first try animating the light direction. Bring it in as a uniform. We'll need the uniform location. And rather than creating an empty vec3, let's create one using the exact same values we were using before. I'm using GeoMatrix here again, but feel free to use whatever library you prefer. Normalize it. Make sure it works. Yeah, it's working. Add a new draw function. use request animation frame to get it animating. And every frame rotated around the y-axis a little bit. And now you get a sense of a light source spinning around a square surface. But remember, this is just a point primitive. What we're seeing here is simply a single color. But it's still pretty convincing, right? So now, let's use an actual 3D model. I created an icosphere in Blender so that we can load it directly into an array buffer for WebGL. The file has the following internal format, which I know because I exported it myself. Here's how it's structured. It contains only floats. Every 32 bytes is a separate vertex containing 8 float 32 values. The first 3 floats are the x, y, z position coordinates. The next 3 floats are the normal vector. And the last 2 are texture coordinates, which we won't be using. I'll probably do a video very soon on how you can make your own files like this. It's really not that difficult. Since we're loading a file, this needs to go into an async function. And put the file loader into its own function. We need a buffer. And bind it. Send in the icosphere data using buffer data. And set up our vertex array pointers. The first 3 floats are our position coordinates. Let's put that into attribute location 0. There are 8 floats per row, so the stride is 32. The second 3 floats are our normal, and we'll put that into attribute location 1. And enable them. So position is location 0, normal is location 1. Now, to our vertex shader. Instead of our hard-coded normal vector, let's use our normal attribute. And, whoops, I forgot we're still rendering a point primitive. Change that to triangles. And the number of triangles can be derived by the array buffer size. And so close. The problem here is that our triangles are being drawn according to their order in the data file. Some triangles from behind are being drawn after the triangles in the front. So they just get drawn on top. We could fix this by enabling depth testing, but it's more efficient to enable face culling. And it's working. And it looks pretty good. Now, we could actually stop here, because this is as much as you really need to know for very basic directional diffuse lighting. I really hope that all of this seems pretty simple. This kind of lighting is just about, again, calculating a brightness value using the dot product of a light vector and a normal, and ignoring any negative values. It's a mouthful, but it's not crazy. So what's left to learn? Well, nothing about this kind of lighting. What's left is what to do when our normals become incorrect. Why would normals become incorrect? Well, let's think about this. This shows how things are supposed to work. This is a basic model in Blender. I have face normals visible. You can see how the normals move visibly with the model, and when the model is rotated, the normal directions, stay aligned, perpendicular to their faces. And when we scale the model in any direction, the normals remain the same size but change their orientation, again, always staying aligned, perpendicular to their faces. What would happen if we tried to rotate our vertex position values without also modifying our vertex normal values? Basically, this. Positions change, normals don't. The normals that are still being used to calculate light values for those moved vertex positions. What does that mean? Well, let's find out. So currently we're rotating our light direction. Let's change things and try keeping our light stationary. and spinning our object instead. We'll need a model matrix for this. First, we're going to apply a matrix transformation to our position. That matrix doesn't exist, so we'll have to bring it in as another uniform. We'll need to send it to the GPU. We'll need its location. Create a new mat4 and send it in. When we create a new matrix like this, it's an identity matrix, meaning it won't do anything yet. It'll just leave the model unchanged, but it shouldn't break anything either. And when we save, there's no change and nothing broke, which is good. Now, stop rotating the light and rotate the model instead. And remember, our light is stationary now, but it looks like it's still rotating in sync with our object. But it can't be, because the light's not moving. What's up with that? Let's go back to Blender. Remember that our surface normals here are used for a brightness calculation. For us, that's their only job, and really the only reason we care about them. If we rotate our model like this, but we don't do anything about our normals, then that brightness calculation for each point on our object won't change, will it? The normal's not moving, so the calculation stays the same. That point on our mesh will stay lit the exact same way, no matter what we do with it now. So here's where we have to start thinking in normals. We've got our lighting calculation working. The dot product calculation is finished. We're all good now. All that's left for us to do now is to make sure that our normals still work, that they still make sense with their updated positions. If we turn our object, what does that do? Or what should it do to its normals? If we scale or translate our object, what should that do to its normals? So from now on, our only job is to think about what the normals should be and what we have to do to make them stay that way. Sometimes our job is a bit complicated, but in this case, the quickest and easiest solution is to simply apply the same model matrix transformation, rotation, to the normals as well. Rotate the vertex position and rotate the normal, and that should work. Let's try that. Multiply the model matrix by the normal and, well, this is a syntax error. A vec3 and a mat4 can't be multiplied. But if we resize the matrix to a mat3 like this, and that works. So in this case, for simple rotation, the solution turned out pretty easy. Apply the same matrix transform as a mat3 to the normals. Let's get a bit more complex. Let's see what happens if we apply a scaling transformation instead. Maybe looks okay at first, but see how the object loses its detail and gets darker? Again, think about the normals. We're scaling the positions, but if we scale the normals, they get shorter, and normals have to have a length of 1. So let's normalize them. And that fixed it. Again, also pretty easy and inexpensive. So in this case, to keep things correct, we had to apply the same matrix transform and renormalize the normals. But now, what happens if we squash our object? This is really the worst case scenario. Here, applying the model matrix to the normals won't work, and normalizing won't help. Stop for a second and think about why. What happens to the normals if we squash our model? Again, here's Blender showing us how it should work. As we crush the model, the normals should remain perpendicular to each surface. By the time it's almost flat, they should all stick either straight up or straight down. But here's what would happen if we applied the model matrix to both the model and its normals. Do these normals look perpendicular? Not even a little bit. The solution to this is called the inverse transpose. Inverse and transpose are two functions commonly used in linear algebra, like the dot product and normalize functions. You can call these functions directly in your shader code if you want. But Because inverse is a little expensive, it makes sense to call it once per frame in your JavaScript, so your matrix math library needs to have it. It doesn't matter if you call inverse before transpose or transpose before inverse, they'll both give you the exact same result. So here's what it looks like if we don't change our normals. Here's what it looks like if we just use our model matrix on our normals. And here's what it looks like with the inverse transpose of our model matrix. Looks exactly right. So let's try this out. In our JavaScript first, let's try squashing our model instead of scaling it uniformly. Next, we'll need a location and a mat4. It doesn't matter which function we do first, but let's start with the inverse. Calculate the inverse of the model matrix. The result will get put into the new matrix. Next, calculate the transpose of that matrix and store the results in that new matrix again. And then send the mat4 to the GPU. When we save, nothing's changed because we're not using the inverse transpose matrix in our shader yet. Start simple spinning again so that we can make sure nothing broke. In our vertex shader, declare the uniform and use it in our lighting calculation instead of the model matrix. And the spinning looks right. Let's squash our model now. That's different, but is it working? Yeah, that's working. That looks pretty flat to me. So yeah, the inverse transpose is what you turn to when you have significant visible deformation in your models. But notice it worked perfectly fine when our model was just spinning as well. So you can safely use this for any model transformation. It just might be a tiny bit more expensive. Time for the last step, smooth shading and fragment shader lighting. Throughout this video, we've been happy playing with flat-looking surfaces, but what if we don't want flat surfaces? What if we want nice, smooth-looking surfaces? Time for smooth shading. Let's pop back into Blender to see exactly what smooth shading looks like and how smooth shading is done. First, I can toggle between smooth and flat shading anytime I want for most objects. And for our icosphere, you can see how it really does a convincing job at making this mesh look perfectly smooth. You can still see this is a low poly model when you look around the outer edge of the object, but everywhere else looks smooth and even. Let's stop looking at face normals now. Instead, let's look at vertex normals. In Blender, this view option is called split normals. This can be a bit confusing to look at first, so let's zoom in on just one face. So here we see things the way that WebGL sees them. Each vertex of our triangle has its own normal. Because we're using flat shading right now, every point of this triangle will have the exact same normal. Let's change to smooth shading and look at what our normals are like now. They're definitely not perpendicular anymore, right? Well, not perpendicular to this flat surface. But if we view the entire object with its smooth shading, you can see how these normals appear perpendicular to this rounded surface. In fact, if we reveal all the other vertices now, we'll see how basically every vertex seems to have only one normal now. In actuality, you're still looking at 5 or 6 normals. It's just that they're all pointed in the same direction, and each normal is perpendicular to that rounded surface, in this case. So there's really no magic to it. We still have the same 80 triangles, the same 240 vertices. Each vertex has an XYZ position coordinate and a vec3 normal. It's just that the normals are oriented differently, oriented perpendicular to the surface we want the viewer to see. Usually, this means having to export a model with the normals that we want to use. If we want to show both smooth and flat shading for the same object, we usually have to include both sets of normals in our vertex data. In the case of our icosphere here, though, we're super lucky. That's because this icosphere is basically a sphere, a low poly sphere, with a radius of exactly 1. So every vertex in it is already 1 unit away from the origin, so it's already a normalized vector. And their orientation, they're perpendicular to the surface. So each vertex position is also its own normal for smooth shading. In fact, if we went through the process of generating normals for these vertices, which I've actually done by mistake, we'd just end up with the same values, or very close to them, as our position coordinates. So we're getting smooth shading normals for free with this shape. So all we need to do is change the normal attribute pointer in our JavaScript to reuse the same position attribute pointer data for our normal to get smooth shading. And we're done. Except, if you look at this long enough, you may realize it doesn't look exactly right. It looks a little lumpy. Not all the time, not everywhere. So what's happening? The long answer, which I won't go into here, is that we're interpolating our normals in the fragment shader without normalizing them. I know it doesn't look like that's what we're doing here, but mathematically that's what we're doing. The short answer, though, is that we're making our lighting calculation in the wrong place. In this case, for smooth shading with so few triangles, we need to make our lighting calculation in our fragment shader so that we can make sure that our normals all have exactly the right length. So we're going to have to move this code here down here. If you're careful about it, this isn't too hard to do. We're not calculating the brightness value in the vertex shader anymore, so that comes out. And to make the calculation in the fragment shader, we'll have to send over the normal information. Our light direction and inverse transpose get moved too. I forgot to take out the point size assignment. And all that's really left to do is to make the calculation and clean things up a bit. It's a lot better now for sure. Still not perfect, but at this scale, with so few triangles, it'll never look perfect. So I'd either switch to an icosphere with an extra degree of subdivision, or not display it so big like this. But I hope that this makes the point. For smooth shading, you end up wanting to make your lighting calculation in your fragment shader, or add more detail to your geometry, or live with a certain amount of lumpiness. Anyways, I think that's it for directional diffuse lighting. It took a long time to get here, but it really is just a simple calculation and maybe a modification or two to your vertex normals so that they're all pointed where they should be. And that's it. I hope that you'll give this a try. I've put some sample code in this video series GitHub repo. Check the video description for the link.